everybody to this special seminar. We have Philipp Eller today from University of Munich. Philipp graduated from University of Zurich, working on CMS before seeing the light, switching to neutrinos, where he got a postdoc at Penn State, and is known for doing neutrino oscillation. In fact, actually, working with convener for IceCube neutrino oscillation. And then a critical component to how we handle data in IceCube. Hypersurfaces, correlations, uncertainties. Developed a novel reconstruction method. Developed one, he's working on another right now as well, contributing to that. And yeah, as many other things, tell us about some more recent work. Many things. So.
All right, thank you for the very kind introduction, Jason. And yeah, it's a pleasure to be here. In this talk, it's kind of a mixed bag of things, but they all tie together because it's kind of an application of, let's say, novel statistical techniques to the field of neutrino physics and neutrino astronomy. And I have organized the talk actually in energies, in descending order. So we'll start at the very highest end with TeV energy and work all the way down to keV or even eV. And so these are the couple different things that I want to show you. We'll start with IceCube alerts and neutrino flares and how we started using unsupervised machine learning that enable us to do self-triggering. Then we'll go a bit lower in energy. I'll show you a couple of ways how we can do event reconstruction in IceCube, and also how we can use novel approaches in Markov chain Monte Carlo sampling for parameter inference in more general terms. Then we'll move down to lower energies. We worked a bit on so-called goodness of fit tests, and we apply them now for supernova triggering. And then in the very end, there's also a fun project we did last year is for the Cartern experiment, which measures the absolute neutrino mass. We started using neural networks to speed up the analysis and yeah, do great things with it. So yeah, jumping right into the first story here. It's a story probably many of you have heard before and are very familiar with, probably more familiar than I even am. And this is something that happened almost 5 years ago in IceCube. We had a high energy neutrino interacting in the ice and creating a spectacular signal. And this is an event display over here. Okay. that you can see. And these blobs are all registered light in the detector, and you can see kind of this very nice track going from the right to the left. It spans over a kilometer in the ice. So this event had a really high energy and also high so-called signalness, which means that we believe it's of astrophysical origin. And what happens then is IceCube is issuing an alert to the community, and all kind of other observatories can follow up this event. And quite a few did over the following hours, days, and weeks. And usually it's quite disappointing because nothing is found, but this time it was different. And actually 2 other observatories found electromagnetic counterparts to this alert. And this actually came from a blazar in a so-called flaring state. And this is summarized kind of in this plot over here, where you see this red dashed line and the gray line shows the localization from IceCube. And then the other observatories, they kind of had to scan or search this region for something happening in there. And then there's a zoom in here from the uncertainty regions from MAGIC, an Cherenkov telescope, and from Fermi, a satellite-based observatory. And they found something that's consistent with our alert position. So this was already very great, but then we went further and we had a candidate source with a known position. And what we did then is we went back on the data that we already have on tape for operating basically 10 years, our observatory, and basically checked if at that very position, was there something in the past data that was of significance? And we looked for transient signals, so a signal that is just appearing at a certain position in time. And we actually found something, and this is summarized in this plot here. This is the time axis. And you see that there is here a very significant excess of events over the background expectation from the very same location in the sky. And we found actually, in statistical terms, 13 events above background, plus minus 5. And they were prior to this high energy alert somewhere in December 2014. So yeah, this makes a very convincing story. And this is just summarizing the whole thing in a small graph. IceCube had an alert. It triggered follow-up searches. The follow-up searches basically informed us about the position of an interesting object, and then we went back into the archival search. Now, if you look at this graph long enough, maybe you ask the question, can we kind of cut out the middleman here? Can we just do it ourselves? So basically, can we do this? We have an IceCube alert, and we can directly go back into an archival search. And the answer is yes, but it comes with a very heavy computational challenge. And one of the biggest problems is that without these partner observatories, we don't really know the precise position. So what we have to do is we have to do and look at all the positions that are allowed. And in some of the IceCube alerts, these regions in the sky are humongous. You can see a map over here with all the alert positions from IceCube that were issued. Yeah, you can see there are events like this, which cover like a really large patch of the sky, and you basically have to scan through everything and do the archival search at every point. And this is not enough. Of course, in addition to that, we have more fit parameters. You have the signal strength, the spectral index of the signal, and the position of this time flare, and the width of this time flare, and so forth. And it is really a horrible space to search in, because yeah, you basically, what you do is you're fitting a likelihood for a likelihood ratio test in statistical terms. And you assume a uniform background distribution, and then somewhere in time, like an excess that has either the shape of a Gaussian or just a box. And so you need to find this position, which is really not a very nice job for a minimizer to do. And yeah, so this is if you write down our likelihood. So it has a signal component, it has a background component, and it's a mixture of these components. Then you think, well, okay, it's a mixture, and I have heard of mixture models elsewhere in a book about machine learning, maybe. And once you realize that, then you think, well, okay, maybe there's something to be learned from the data science perspective. And mixture models is something that's quite old and quite textbook. And there is a very special method that is used to fit mixture models, and it's called expectation maximization. So I want to try to explain you in a nutshell how it works. Right, the technique comes from so-called unsupervised machine learning or clustering, and it's very similar. Maybe some people here are familiar with k-means clustering and the Lloyd algorithm. If not, doesn't matter. But it's basically a soft version of that. And the way it works is the following. I tried to make this animation here. So this is just now fitting to a couple data points here in this axis, two Gaussian distributions. These data points are generated from these two Gaussians in the gray dashed lines. So that's the known truth, and that's what you want to infer. And the way this algorithm works is you just start with a random initialization, and then you can actually see it will come back in the animation. It's just like through two completely wrong Gaussians on there here. And then it's an iterative procedure. What you do is for each sample, you just take the assumption that these two random Gaussians are the correct solution. You calculate the probability of each sample belonging to either of the two distributions. And that's shown here. The ones that are thought to be of the blue distribution are shown in the blue color, and then the one from the red in the red, and in between somewhere is a white color. And then having these weights, you update your model parameters by calculating the weighted mean and the weighted standard deviation from these points. And that gives you just your new definition of the next iteration. And you can see, even in this very simple example, that this type of fitting is extremely fast. You see that after like 10 iterations, you converge, it's stable, it doesn't change anymore, and it's very, very close to the true solution. And if you were to try that with a different minimizer, you immediately run into problems, because this is a horrible space with a lot of local minima, and it's very hard to minimize. But with this technique, it actually works extremely well for this type of problem. So we thought, well, okay, let's just apply that to our problem. It's slightly different. Okay, here we don't have the mixture of two Gaussians. It's a mixture of one uniform distribution and one Gaussian, but it works extremely well. It's extremely fast. And this is just one example. So this is from simulation, from IceCube. So you have here the time axis of different events. And we injected a neutrino flare from simulation here in orange. And you see the result of the fit here. And it finds the flare. It's just one example, of course. And yeah, it's actually even more cool than that, because you can easily extend it to a multi-flare search, because it doesn't matter how many Gaussians you throw in there. So what we did here is we injected signal at 3 different positions, and we fit just 100 Gaussians to it, because it doesn't matter. Most of the Gaussians are fit to 0. Some Gaussians, they of course describe some statistical fluctuations in the background, but even more importantly, you can also, again, correctly identify these 3 neutrino flares. So this technique actually gives us now the capability of doing these kind of searches. And then we went and applied it to real IceCube data. And yeah, it's speeding up the analysis by orders of magnitude in time. But we basically reanalyzed our data. And what we then found is basically, again, this Texas flare, just with our method, and without using this localization of partner observatories. And you see here, this is basically the same plot I have shown you in the beginning. In the gray dashed line, this is the official analysis from IceCube. And then in the black dashed line, this is the solution from our fit. And I mean, it's extremely well consistent. It's actually also quite nice to see that we get the same neutrino flare out of the same data with a completely different method. Right. So yeah, now it's going to be a couple of different topics. And we'll, yeah, you can actually ask questions maybe in between. Yes.
Collaborator, so I get a chance to talk to you all the time. So this opportunity now with everybody. How would this be different than a variable bandwidth KDE?
The variable bandwidth KDE works in the following: that you would take the position of each event and you would put a Gaussian at this position. But that's not what we're doing.
Right, but then you maximize or minimize the width of the KDE.
Sure.
To then create.
Yes, I mean, you could do that, I agree, but then it might be a bit harder to interpret if you have a flare or if you not have a flare, because you could probably have something in between, because the KDE would probably just give you a time profile that has maybe a couple wiggles in it and maybe a slight excess. And this is really just a 2-hypothesis test. Either there is one Gaussian and a uniform background, or there is just a uniform background. So you get like a classical likelihood ratio that you know how to deal with. In the KDE case, I think it would be maybe a bit more difficult to, you know. Yeah. Yes. Well, I mean, even in this case up here, of course, you need to do also background only trials, and it will always find a solution that has some flare somewhere. The question in the end that it boils down to is just, is it a significant excess or not? So basically, you can do these background only trials and see how kind of fake solutions look like, and then you can gauge how significant is your actual observation. And that's what we're doing. And in the case of the IceCube observation, it was then determined that it was quite at the threshold. It's just significant enough to be something that is not compatible with background. Yes. Yes. Yes, yes.
So how do you find the optimal number?
Yeah, absolutely. Yeah, I mean, there's more fit parameters for every Gaussian. You can have an amplitude.
Yeah.
So you get an overall, we call it NS, the number of signal events. And that is a fit parameter as well. So yeah, actually here, yeah, we put 100 Gaussians just for fun, and most of them fit to NS exactly 0. So basically you can discard them. But yeah. Yeah. Yeah, so I mean, you have to be careful how you choose your initial configuration, of course. And what we do here in this one Gaussian case, we take a Gaussian which is extremely wide, which is basically uniform. So we take, I don't know, it's like 1,000 base width or even more. And then it doesn't really matter where you put it. And of course, we did a lot of like round trip tests where we inject signals at different positions and see if we can recover them at the correct position, and signals of different width. And we can show that we can always find a solution that converges to the correct position once the signal is strong enough. Yeah. Right. Maybe if there are no other questions, I think we'll just move on to the next topic. Should we close? Or it's probably fine. Which is connected to the topic I just shown you, which is about event reconstruction. And I'm going to show you 3 different approaches. So this is basically what I showed you for this plot up here. How do we actually know that this alert came from this position in the sky? And this is the process of event reconstruction that we're doing. So we're basically trying to infer per event parameters in our observatory. And this per event parameters, they could be the direction below the energy, the position in the detector where the neutrino interacted in, or the type of event. Was it a neutrino? Was it a muon? Was it something else? And you could summarize this data also in this picture here. Here you have an event. You have these strings from IceCube, and each kind of gray dot here is a sensor. And if the sensor receives some light, it is represented as a colorful blob. The size of the blob is basically the amount of light, and the color of the blob is the timing of the first observed light in that dome. Early is red, late is blue. So you can see by eye already there is something that started here and went over there in the track. And yeah, you're basically trying to infer this direction here that is shown here in this arrow, or the energy and so forth. So this is basically the task at hand. And this is an event at 290 TeV of energy. And then before I mentioned that we keep going lower and lower in energy in this talk. This is how an event, for example, in 25 GeV is looking like in IceCube. And this is actually in the center of IceCube in deep core, where there's a more dense spacing of strings. And there's much, much less information there, which in some sense makes it a harder task to do the reconstruction. Yeah, but we have found ways how to deal with these events. And the first one, this is actually something I did a bit longer ago. But I want to include also this approach because it's kind of like the textbook solution, I think, that you would apply is the following. You write down a likelihood, then you try to write it down, and you find out, oh, it's intractable. Then you start doing approximations to kind of get this likelihood as good as possible. And then once you have the likelihood, you can use it in standard inference techniques. So we did that, and this is just a comparison of our approximations to the true likelihood, and we nailed it down to something that is quite good. And once we have this likelihood, we can do inference. We can, for example, use and optimize it to find like their so-called maximum likelihood estimators in frequentist language, to find kind of the best solution given your likelihood landscape. This is just showing a plot of an example of how these likelihood landscapes look like in slices of 2 dimensions in the space. It's an 8-dimensional space. And yeah, and for the example event, I think the true location or position is in this black crosshairs, and then the maximum likelihood estimator is this white star marker. And this works fairly well. And yeah, we also wrote a paper recently about this. This is just showing you the performance in a couple of plots. This is always like one of the variables that you infer, like the x position and the azimuth angle, the total energy and so forth, as a function of energy. And you want to stick as close as possible to this line at 0. And it works well. It works down to just a few GeV range. We have a pointing resolution for so-called cascade events for order of like 10 degrees, and for tracks it goes as low as about 1 degree. The higher the track energy is, the better the pointing gets. And the only problem with this method is that this fitting is rather slow. So per event, on average, you have about 40 seconds that's needed to find a solution. And we have many, many events in IceCube. So in the past couple of years, we were thinking of ways how to deal with that and how to make it better. And of course, the answer is machine learning. There have been several machine learning architectures used and proposed and implemented in IceCube. And there's a very nice paper that was published by collaborators, I think a year or two ago, about how to do it for high energy neutrinos. But now we also want to figure out ways how to do it for low energy neutrinos. And yeah, so I mean, there are people in this room that are really the experts here. And we actually have this workshop right now on this topic. But what we found is that using a machine learning architecture that's called graph neural networks suits us very well. And we just represent these so-called pulses, so these colorful blobs from the picture before, on basically a mathematical graph. And then you do a cascade of so-called graph convolutions, which is shown, actually I have an animation here, yeah, graph convolutions of these input nodes to correlate them together with these convolutions. This is the convolution operator that we're using. And in the end, you put them all in kind of a classical neural network, just a dense neural network to converge everything into one single number that you try to regress. And yeah, this is done by these aggregation functions. And you can use that to do regressions of different variables, the energy, the angle, and so forth again. And this works really well, and it's already outperforming this likelihood reconstruction that I showed you before in some part of the phase space at least. And in particular for cascades and short tracks, we can already see now kind of a gain of 10 to 20% in resolution. This is also shown on the plot over here. This is showing the ratio of the graph network to the likelihood reconstruction. And whenever this ratio plot here is above 0, you're winning. And we're winning most of the times. And we're pretty confident that we'll also soon fix this problem here and just be better than likelihoods in general. But I think much more important also is what we call the inference speed. So how much time you need per event. Before I told you for the likelihood reconstruction, we're actually measuring it in seconds per event. And now with the graph network, we can measure it in events per second. And yeah, you can see, I mean, it's orders of magnitude faster, which is great because it probably will even allow us to do this online on the detector data stream. And yeah, this is for online reconstruction. So this was the second technique. And then I just also want to show you the third technique, which is kind of a blend of the first two. You could think of it as a hybrid of likelihood and machine learning. And basically what we do here is we just use machine learning to approximate the likelihood function. And then we can use the standard other tool chain to do the inference for us. Yeah, as I said, the likelihood for reconstruction is in general intractable. And we have to either resort to approximations, but it turns out there is a very neat trick. There is a couple of things that you need. And in particular, you need so-called forward simulation. So basically the ability to artificially generate events that look like data. And we have that, of course, in IceCube and in many other particle physics experiments. It's something you have. But then the trick works like as follows. You just simulate a set of events distributed according to a prior distribution that you choose. So you say, well, I produce events with these energies, with these angles, with these blah, blah, blah. And then given these parameters that are called theta, you create random variations of the theta x that you could observe in the detector. And you call then that set that you produce PA, which is basically the joint probability of the data and the parameters of the model. Now you put that set aside, and then you make a second set, which you call PB, and statistical formulation is shown here. So this is basically just the multiplication of the probability of the data times the probability of the parameters. Now I think, well, how do you produce this set? That's actually very easy. You take the this set and you break the correlation, and then you get this set. And you can break the correlation by just doing random shuffling of x versus theta. So this set comes for free. And now this is where the magic happens down here. If you train a classifier, so the black box that tells you whether it thinks an event came from set A or from set B, and if you have the optimal classifier, there is a mathematical proof, and the optimal classifier here is called E star, that then the odds ratio of that thing is the exact same as the likelihood, which is that thing, divided by the probability of the data, which is also called the evidence in Bayesian lingo. And then you're almost there, and then you realize that if you do inference, the only thing that you care about is basically theta, that's a variable, and x is a constant, then that thing down there doesn't matter because it's just constant. And then you have a thing that is proportional to likelihood. And yeah, I mean, the event reconstruction is just one example of this technique, but I think it's just applicable to many other things where you want to do inference and don't have access to the likelihood. So we tried that out for event reconstruction. If well, this is from before. I didn't really explain that well, but basically we just train neural networks to approximate the different parts in our likelihood with the technique shown before, and then we sum them up and we get the total likelihood. And this is how it performs like in a two-dimensional toy example. We chose a toy example because we know the exact truths that we put in there. This is the toy example shown here. It's very similar to Gall's lighthouse problem from the statistics textbooks. You have kind of a number of sensors along this line, and then you put a source of light somewhere, and you want to infer where the source was. And we have done that. We have trained the networks, and here is an example of the likelihood landscape, comparing the known truth in the dashed line to our approximate likelihood in the solid lines for a couple of different examples. And I guess you could convince yourself that the technique is doing the correct thing. And yeah, so this is yet another technique that we're using to event reconstruction. And yeah, we're applying this to IceCube, but also to other detectors like Watchman and EOS, which are smaller water Cherenkov tank type detectors. And it works quite well so far. All right, so I don't know, maybe I should also stop here for questions before we move to, again, a slightly different topic. I think Thomas first. Yeah. I think we're pretty convinced that we're not losing too much in the minimization process, because also, for example, in this freedom, we're using the same minimizer, and we do a lot of studies. How does it change if we include many more seed points, or if we do other types of minimizations? But I think that's not where the gain is at. I think it's much more in the incorrect approximation of the likelihood in some parts of the phase space, I would think. But yeah, I don't know, maybe also other people here in the room that work on the GraphNet have some better intuition of where we're gaining. It's also, I mean, it's also interesting that yeah, if you look where we're gaining, it's basically for cascades and very short tracks. And we are not, at least at the moment, not gaining for longer tracks or extended tracks. And it could be as simple as not having enough training data there, or there could be something more fundamental or limited. But yeah, I think we're very soon going to find out, because, for example, Rasmus started also reconstructing higher energy events, which I think will give us maybe some information where. But yeah, I don't have a good answer for you, unfortunately. Yeah, sure. This one? Yes. That's correct. Yeah. Yes, I mean, so it's a composite hypothesis basically. There is always a cascade and always a track in the fit, and they both have a scaling parameter for their respective energy. So irrespective of what type of event it is, you apply the same reconstruction. And if it's truly a cascade, it should, in principle, put the track energy close to zero and put all the energy into the cascade and vice versa. But doing that also gives you kind of a handle on, for example, inelasticity of the event, which some people have started looking into. And I think Tom produced a couple of studies. And there is actually, yeah, some correlation to the actual inelasticity in muon charge current interaction, for example. Yeah. This, yes. Yes. Yeah.
Yeah, I guess my other question is, do we ever have this kind of sharp
Yeah, I mean, it's actually a problem that we have noticed quite often, that kind of sharp features in the likelihood landscape are extremely difficult for the neural net to approximate. And we have also tried out kind of like different activation functions to get something that is much more nonlinear than like a standard derivative or something like that. But ultimately, what we think is the fundamental problem is that if you have such sharp features in the likelihood landscape, it basically would mean that in the training data, you have a lot of events in that place, or almost non-events in that place. And that's never quite the case. Or it's never as sharp as the true likelihood would look like. I think that's really the problem. Luckily, though, if you like focus on the places that are important to converge to the true solution, the likelihood landscape usually is more shallow, because I mean, usually these sharp features are exactly aligning with the positions where we have sensors or in between, and usually you're not there with your event. Usually you're somewhere else, so there it's maybe a bit better behaved. And it's not that important that the likelihood is worse by what exact number. It's just important that it's worse at that place, right? So kind of like a sharp hole in the likelihood landscape. If it goes down to minus 1,000 delta log likelihood or minus 500, doesn't matter again. But yeah, we are also kind of concerned and try to fix this. Maybe I'll just keep moving on then. Okay. Now, yeah. Parameter inference. Yeah, this also is connected to the last thing, because I didn't really tell you how you do parameter inference, just that you have a likelihood now. But yeah, this is a common problem, I think, in all of data analysis, that right, we have at best usually a likelihood, or just a model with parameters theta, and we can sample X from it. So we can sample random variations of the data, but usually what we want to do is the other way around, right? We want to inference. So basically we have a set of data and we want to learn the underlying event or the underlying model parameters from it. Even if you do some other type of analysis, you want to figure out what is the property of that black hole, or what is, yeah, whatever. So there are two schools. You can do frequentism or the Bayesian framework. I want to show you a couple of things about doing the Bayesian way, because it's usually less used, at least in our domain. And what you do is use Bayes' theorem, which is shown here, that kind of connects your likelihood here. This is the probability of X given theta into a probability of theta given X. That's what you usually want to learn, and then you find that out and write a paper about it. And nobody's writing papers about that thing because it's kind of boring. So there's a couple of things you have to put in there. One thing is a prior that always is the cause of discussion, but let's just assume we have a prior. And then there is this horrible thing down here, which you can just like say, it's just a normalization, I don't care, but it's a very complicated integral usually. And it kind of turns out to be very important. Yeah, the integral can be an extreme challenge to solve. And it is needed as a normalization constant, because otherwise you'll never get access to the posterior distribution, because this needs to be a probability distribution that's correctly normalized. And even in its own right, this integral can be interesting because you can do stuff like model comparisons with it to construct these so-called base factors. So, but then how do you solve this integral? Well, luckily, quite a while ago, people thought of something that's called MCMC sampling, Markov chain Monte Carlo. And there's a neat trick again. If you evaluate just a point in your model space, theta trial, versus another point, theta reference, and you calculate the probability ratio, so the odds again, the integral cancels out because it doesn't depend on theta. And then you can write down this expression, which does not include the integral. Having that, you can now create a so-called Markov chain, which does the following. It's kind of a chain of points in the theta space, and you move from one point to the next by proposing a new point according to a so-called proposal distribution. But then with these 2 points, you calculate this odds ratio, and then you apply a specific accept reject condition. And if you accept the point, you take this, and then you go further from this point, or you just stay in the point you have. And if you do that correctly, you obtain samples that are distributed according to your posterior distribution. And you never needed to solve any integrals on the way. And this is great. This is kind of the idea behind MCMC sampling. But sometimes, as I said, the integral values are anyway needed and interesting. So can you still do the integral? And yeah, there are several approaches that exist. There's, for example, nested sampling, there's bridge sampling, and so forth. However, they have a couple of drawbacks because they basically need you to perform additional computation that can be expensive. So we wrote a paper, I think it's actually now 2 years ago, how you can use existing Markov chain Monte Carlo samples. So you sampled your posterior anyway. You just take these samples, plug it in our box, and our box spits out the integral value. And this works like the following. You have, let's say, your samples that are shown here in this distribution. You then slice it up into smaller chunks. You choose regions that are favorable for calculating the integral. And then you can calculate the integral in these regions using harmonic mean, which is a specific techniques how to estimate these integrals. And then you can use all these different values to calculate an overall value, including errors and so forth. And this we call the adaptive harmonic mean integration. This algorithm, we tested it up to high dimensional target densities, and it works surprisingly well. We get reliable performance for integrals up to around 21 dimensions. And we have tested it for different distributions, for normal distributions, which are kind of easy, let's say, Cauchy distribution, which are known to be pathologic. The so-called funnel distribution, which is a standard performance measure in Markov chain sampling, and also these Gaussian shells, which are in higher dimensions, then get very complicated. And you can see here as a function of dimensionality, we get very reliable estimates for the integral value, including error estimates that kind of check out. Having that in our pocket, we then could move on one further step and use that algorithm to do one more thing, which has to do now with parallel sampling and multimodal distributions. And these are common problems in MCMC sampling. In case you're familiar with MCMC sampling yourself and maybe tried it out, maybe you noticed that it's kind of an inherently serial process. And it can be a problem because maybe you just cannot wait long enough to get the solution. And every time you need to evaluate the point, you have to wait for the previous point to finish. You can run multiple chains, but still there's a lot of problems associated with it. Because for every chain, you need to reach convergence for detailed balance, blah, 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 blah. And then this is one problem. And another problem is sampling so-called multimodal distributions. So there are distributions with more than one separate peaks. And basically all these Markov chains, they have the problem they get stuck often in one peak, and then you get garbage result. And this actually is important also for us in neutrino physics, because we expect multimodal distributions, for example, in theta 2-3, for example, in the mass order and so forth. And it's a real challenge to do MCMC sampling in these kind of spaces. So actually, we found out we can do the following. We can slice the space apart into different regions. We sample each region individually. What you get then is kind of shown here in the gray histogram, which has the right shape, but the wrong normalization. But then what turns out is if you're able to calculate integral values, you can calculate the correct weights and stitch everything together. And I've shown it before that we now have this machinery for the integral values, which gives us the capability to calculate these weights. Then if you stick that together with these weights, you get back the red distribution. That's what you wanted to sample. So the problem is really, again, like a couple different steps. Let's say you have a complicated distribution like this over here. It's just in 2 dimensions for visualization. There are 4 separate modes. And what you do is first, you need to figure out how does your space roughly look like. So you just do some sampling. It doesn't even matter if it converges. It doesn't matter. You just want to find where are some region of probability density is non-zero in your space. You do that. Then you do so-called space partitioning, where you automatically slice the space into chunks, and it should also separate these modes. You have come up with an algorithm that does that, and it creates a picture like this. Then you sample each region individually, and then you plug it back together, and you get this very nice posterior density from the distribution you plugged in. And then what we actually found out, and this was even a bit surprising for us, that doing that, we get even better than linear scaling in parallelism. So you're actually better off taking a density, slicing it into spaces, sampling the spaces individually, and then putting it back together, which maybe sounds a bit surprising, but actually what turns out is that in these smaller spaces, it's much easier for these chains to converge or to be tuned. And yeah, we have shown this here on the plot over here. This is showing you, for example, the number of spaces you produce and the time you spend sampling each space. And you can see that, for example, having 4 spaces and sampling for 3 seconds in each space gives you a better result than having 1 space and sampling 15 seconds in that space. So you spend less time overall and you get a better result. But these numbers should be as close to 1 as possible. You see this is closer to 1 than that. And so it gives us also better accuracy of the estimates. We check that for all kind of different distributions and all kind of different dimensionalities. So for example, 9 dimensions. And you can actually, with this technique, correctly sample multimodal distributions. It also allows you to, for example, use Hamiltonian MC as the sampler, which is known to not being able to handle multimodal distributions. All right, let's see if there's questions to this part. Yes. Yeah. So it's actually, I mean, the speed up is not coming from this. The speed up is just because it's easier to sample in a restricted space than in the global space. But yeah, you're bringing up an interesting point, because there's another thing we noticed with the first algorithm, the integrator, that these hypercubes in higher dimensional space, they become very, very strange. All the volumes in the corner and nothing is in the middle. And yeah, that's why basically I showed it before, the integration only works up to something like 20 dimensions. And we have started switching out these integration volumes with either hyperspheres or these shells. And by doing that, it works much better. Yeah, so it's an interesting point. Yeah, these things get super weird in more than 3 dimensions. It's very spiky. Yeah. Right. How much time do we have? Oh, okay. Okay, maybe I want to do this, but maybe fast because I think it's fun. It's this is kind of a question for you. Is it uniform? Yes or no? These are 2 distributions of events. Each has 15 events between 0 and 1. There's just, of course, random examples. And the question is this uniformly distributed? And is this uniformly distributed? You can maybe think for yourself which one is, or is none of them, or both. And yeah, here, so this is spoiler. A is uniform, B is not. Or at least it's drawn from a uniform distribution, B is not. B actually has a uniform and kind of like a Gaussian in the middle. Some additional events. So, but how can you tell? So maybe if you're a physicist, first try is to just throw everything into histogram, do a chi-square test. Chi-square is not at all applicable here because you're in the deep Poisson regime, but you're a physicist, you don't care, you do it anyway. Yeah, you do that, you calculate the p-value from the chi-square test, you chose like 5 bins, it tells you, well, this is consistent and both are uniform. And you think, well, maybe I didn't use enough bins, right? Maybe I need 2 more bins. So you do 10 bins, 30 bins, 100 bins. At some point, none of it is consistent anymore, and you get p-value of 0. So yeah. Right, we're physicists, we're smart. Okay, binning is not working. Can we do an unbinned analysis, right? Let's try it. Let's write down the product likelihood of all samples. The product likelihood looks like this for all samples in unbinned analysis, and then you realize it's a uniform distribution you're testing, so p of x is exactly 1. So this thing is always 1. So yeah, congratulations, you did exactly nothing. So yeah, so you go further down your textbook, and then maybe you find something that's called the KS test, which is so-called non-parametric goodness of fit test. And you throw that at the problem. The KS test is doing the following. It's comparing the so-called EDF to the CDF. It's an empirical distribution function to the cumulative distribution function. One is from the data and one is from the distribution you're testing. So you're getting this picture here, and you're quantifying the maximum deviations between the two. And then these guys, they were very smart. They worked out the distribution of this quantity, and that allows you to directly convert it to a p-value. And then this thing test tells you that A is probably not uniform, but B is, which is exactly wrong in this case. Of course, I mean, it's just one example that it shows. Okay, so maybe you think, well, there are other EDF tests. Let's try them. There's all kind of different tests, but they basically just do a different weighting of your events. There's like the Kramer from Mises test and there's an RN test. But bottom line, they all don't really work. And then you go further down the rabbit hole, and then you think, well, there is a feature of the data that I have not yet fully explored. And the data, actually, you can order it, because you can just say, yeah, the sample with the lowest value has order 0, the sample with the second next higher value has order 2, and so forth. You just order them. Maybe you can do something with this. Turns out, yeah, people have thought about this. There is an expected value for each ordered sample, which is just the kind of equidistant distribution. You do this, you calculate the distances to that, and calculate, cook up some test statistics. All of them have names according to the statistician that came up with it. There's Pike and Brink and I don't know what. But yeah, it's very similar to the KS test, actually. Then you think further, and then you think, well, there's actually space between samples. Maybe that can tell us something. And there's these spaces you can construct, right? It's just like the room between 2 consecutive samples, and you can throw in some edges to the left and to the right. And maybe you can convert that into a test statistic. And it should be something trivial. You could just add up the spaces if you always want. So you need to take either the product or the square. You do that, and this also has been worked out with a guy called Moran, who did basically the product of the sum of logs. There's a guy called Greenwood, who did the sum of squares. And yeah, you can do that. And well, it's still kind of disappointing because for this example, which I constructed, it still gives you the wrong answer. And the problem is basically that these test statistics, they're all invariant under reordering for spacing. So basically, we didn't learn much more. So we thought about this a bit more. You can throw in higher order spacings. This has also been done. You can just do like, what is the spacing between not consecutive events, but 1 more or 2 more or 3 more. You can do that. It also has been done by guy named Cressy. And then we thought, well, it's just like, let's take this one step further, go even more crazy, and we call it the recursive spacing statistic. So basically it means you're not only just using simple spacings or spacings of next to nearest neighbors or next to nearest neighbors, but all of them. And you throw them into a new test statistic that we call RTS, recursive product of spacing. And this is now our test. Of course, you have then to work out the distribution of this thing to calculate p-values, but we did all of that. And just jump, oh no, actually this is the p-values down here I want to show you. So for this example, it correctly identifies A as uniform and B as not uniform. And the reason it works is because you see these events kind of from the Gaussian in the middle, they're clustering together. And we're resolving that correlation structure of neighboring and next to nearest neighbors and next to nearest neighbors. And we all convert it into that test statistic. It's also illustrated in these graphics that show you the contribution to the test statistic depending on the spacing ordering. Anyway, so this kind of works well. We compared it to all these other tests here. Not so important, but we found that if you have something that is mostly uniform, but there's kind of something non-uniform in there, it works quite well and it works better than other tests. And other problems, of course, other tests work better than our tests. So it's kind of like we're not doing better than anyone else everywhere, but in some cases we do better. Yeah, but we found some applications for this, and it's actually for supernova triggering. Because what you try to do there is you try to detect an excessive events over something that is otherwise usually uniform. So this is showing you an example. You have a uniform background here in blue, and then you have a signal from a core collapse supernova at a distance of 10 kiloparsec here. And this is an example for a cryogenic detector, ResNova it's called. This is what you expect, and then you can do random simulations of that, and that's what kind of the data stream would look like in your detector. And you want to detect that there is something here that is looking different from a uniform expectation. And you want to do that for very, very low p-values because there's restrictions in these supernova early warning networks that you cannot have too many false positives. So you can not have more than one per week. What usually is done in literature or in also experiments is you create windows in your time, and then you just do a simple Poisson test of the rate. And it works well. And it's great. And this Poisson test can be extremely sensitive, but there is a couple problems with it. It's extremely sensitive to kind of find the correct fine tuning for it, because you need the correct window length for your signal. You need the correct background expectation to calculate the p-values. If any of this changes, then basically the test is not optimal anymore. But anyway, so first we compare towards an optimized
Okay.
Questions that might not have been asked. And,
Yeah. Thank you, Philipp, for the nice talk. On the uniform exercise that you practice, when the talk, I feel a little agnostic about it because conceptually, any distribution is equally likely to be generated from a uniform distribution by definition. Like any possible sample is equally likely. That's why most of the tests in principle fail because they can always be. That doesn't have a lot of meaning unless you compare it with an alternative distribution.
I do not fully agree. I mean, of course, these are like one hypothesis or two hypotheses tests. And of course, you can make a statement if a realization of some samples is more or less likely being uniformly distributed. If all the events are exactly at zero, it's probably not for the uniform distribution, but from a delta function at zero, right? It's a fair statement. So I think there's some use for these kind of goodness of fit tests. They're called goodness of fit tests if you just have one hypothesis, not the way it's called.
That's true. If they are all at zero, it's probably related by a delta function at zero. But I think that imposes that you're comparing with an alternative model. In that sense, it's more convenient to look for clusters, bulk clusters.
Well, I mean, I think again that it depends what kind of statistical school you're coming from. We're just calculating p-values. And the p-value just tells you how compatible is it with the null hypothesis. It doesn't assume any alternate hypothesis. How you then interpret the p-value is another question. And maybe there it's important to assume an alternate hypothesis to correctly interpret the p-value. But we're just giving you the p-value. Of course, it's still possible you get a p-value of zero and still from a uniform distribution, of course. It's a very definition of the p-value that, let's say you say p-value 0.05 is my threshold, then you just say this type of error is very rare. But of course, yes, all the samples are in principle possible.
Just a last question. How many events were expected from the triggers of these supernova signals?
Well, okay, it depends how far away the supernova is. Right? I think the background rate is in this detector 0.18 counts per second. So yeah, we can add actually the background. What is it? Yeah, this is a window of here 30 seconds, and you have, I don't know, maybe 10 background events. Yeah, there's 0.18 hertz from background. And then the signal, it depends how far away is it. Here it's 10 kiloparsec, which is somewhere in the middle of our galaxy. You see it's maybe, I don't know, 20, 30 events. So yeah, I mean, it's relatively low counts.
So this is a trivial problem. Like, is it close to the problem we discussed in the first time we talked about there search in IceCube? Like, of course, it's not a Gaussian mixture, it doesn't different shape, but could it apply similar techniques to the first model we talked?
You could, but I think the big difference here is this is kind of an online analysis, and the other one is kind of an archival analysis. The first one, you have the full data set, and then you fit your signal to it. This is a thing that you continuously want to update with new events coming in. So this is kind of a conceptual difference. But I agree that maybe you should actually try it, apply the first technique.
This example was like 40 uniform distribution or not. This one here. So I kind of assume that the reason why the left one, which is actually an underlying uniform distribution, is this long and where you do not have emission. And now, if I understand your method correctly, you are only looking for distances between events, and that basically ignores the last part. Is that the basic?
No, we actually we have what we call the edges at 0 and 1.
Okay.
And then actually, so if you look here at the first row of this picture, the color basically tells you the distance between, or the space between events. And you see here the largest space is this one here on the right, this yellow color. And the smallest space is basically this one, where these two events, you can almost not tell them apart. You get a dark color. And the thing is that these two things here, for example. These two cases or events are very close to each other. They're spatially separated from each other. Whereas over here, there is no such extreme case of two events very close. But here in the middle, you kind of have a lot of events that were moderately close to each other. And so basically, if then go to the next level, this is kind of the next to nearest neighbors. They're still very close to each other. That's why you kind of start building up a much higher test statistic value than on that case where kind of the distribution of the spaces is kind of random. We call this one uniform distribution. And that's where basically the information is gained from. But that's also, by the way, the reason why, for example, KS tests fail here, because this distribution is kind of like proven.
Yeah, which is maximum.
Exactly. The KS test is extremely sensitive to these kind of things, and our test is much less sensitive. So if that's what you want to check for, don't use our test. Use, for example, Anderson-Darling. Yes.
So the computation time that you put in one of the last slides, is that for doing the analysis only? And if it is, what then about training the network in the first place?
Yes.
What kind of computation targets that we have?
Yeah, so there's some, yeah, of course, this is just the inference. You first need to generate the simulation, then you need to train the neural network, and then you need to do this. Like generating the samples maybe one day, training the network is a couple of hours. So yeah, it's okay, it's maybe unfair. It's 1 day plus 1 hour plus 1 minute. But it's still faster, even if you have to create the sample train everything, than to do the inference in the classical way. Yeah.
So, the question: if you go back to your slide 40, yeah. So, if you wanted to find out without using your method that the left one corresponds to an underlying uniform distribution, you could always generate very many realizations out of that distribution and then compare how likely it is that you would have gotten the one you got. Maybe you can bin in the x-axis variable and do some kind of
that's basically it's basically this.
yeah. So
I
I'm failing to see. I mean, I know it doesn't work, but I'm failing to see why.
Because basically, if you have your bins too big, you lose a lot of information.
Right.
Because you just reduce the information of 15 events down to like 5 numbers. Maybe these 5 numbers are not that meaningful to test for uniformity. It's basically, it's always these tests, the name of the game is basically, you have a realization of events and you need to turn it into so-called test statistic, which is just a fancy word for a number. So you also need to map a complicated space into one single number. And you want to kind of have it's called like a sufficient test statistic or unbiased test statistic and so forth. But they don't tell you in the textbook how to do it. So that's why basically all these people come up with different ways how to compute such a test statistic value. And yeah, it just turns out that doing the binning, in the end, we also converted it into one single number, but it's just not the best way to do it.
Right. Okay. Now, I guess my main question is, how do you know that you're using the right one? You don't, right?
Yeah, you don't. So it would be nice if there was a way how to do it, like I don't know, this lemma that the likelihood ratio is the best test statistic for hypothesis comparisons. But here it's just a one hypothesis test, and there's no such thing.
Right. Yes.
We're not at all.
All right. So, no other questions? Thank you again. And I know that folks will be around till tomorrow evening, so let us know if you want to, chat with them about anything else, or I guess we'll probably grab your slides too, because a lot of references that you have to papers.